Okay, let's start. So the title of my presentation is Creating Digital Twins of Embedded Devices with Firmware Emulation. Short introduction about me. So I'm Thomas. I work as security consultant for embedded devices mainly. And I'm focused on embedded systems and IoT security and reverse engineering. And I was previously speaker at Pack in the Box, Black Hat Asia, and some other local and also international conferences. For this talk, I'm not as part of my main employer here because all of the research was done during lockdown, during Corona, and such stuff. And it was not really backed by my main employer, so it's now my own think tank under the flag which I'm presenting, and that's the way how I do the firmware emulation research. So that means this time I'm a firmware emulation researcher, and in cooperation with my main employer, of course, I produced a lot of security advisories just based on emulation of embedded devices without the hardware. If you want to contact me, my information is printed here on the screen. So my short definition of a digital twin is, during this session, a full functional emulation from the operating system of the embedded device, which I want to which I want to look at, which I want to do reverse engineering to, and all of that excluding the physical inputs and outputs, of course, because if you do emulation, then it's really hard to turn on the camera picture because, there is no CMOS sensor and you cannot look at any live stream. Here you can also see a scan of an emulated device. And for me, it's always when I scan a real device and I get out the same results as for the emulated device, then I know, okay, the emulation was really good and works pretty well. So short outline of my talk. The first thing is the motivation. Why do we want to do emulation of embedded devices? A short introduction and basics, also emulation issues, then digital twins, so that I have prepared for this talk, which are running in the background. Of course, vulnerabilities and the whole evaluation, and a short conclusion. What was the main findings of the whole research? What do you see? What can we see if we conclude those firmware emulation things? So, short motivation, the proof of competence, really important. So I want to show I can do it. We can do it. Basically, everyone who's able to develop embedded systems and plays around with stuff like that can do it. And of course, security testing, that's really important. If you can see this picture with this camera, where the camera is out of reach, so you would need a ladder or another possibility how you can unplug and replug and reset and do stuff like that on the camera. It's really good when you do security testing on infrastructure that you have an emulation, because if you break the device, maybe temporarily, so that you need to press the reset button on the physical hardware, then you need to reach the device, and that's sometimes really hard, and also for industrial environments. And you can imagine some devices, some IoT or IIoT devices are out of reach, and it's really hard to reset them. also because of Corona, that's another thing. If you cannot go on site, then you have to do the testing at home or in the office of your employer. And yeah, in that case, you can also use it. It's also really, really helpful. And also for producing advisories without the hardware, of course, and for research and development. So for research, I've used it, those firmware emulations, for doing a lot of advisories, also for researching how was the embedded device in scope developed. Does it use some specific libraries, or does it use some exotic web servers and stuff like that? And how they work, of course. And for development, it's sometimes also really, really useful, because you can add functionalities to the firmware, to the embedded device. You can cross-compile, for example, a binary and add it to your embedded device, if it's possible, of course, if the file system is formatted in the right way, and so on. But you can compile binaries and add functionalities to your embedded system, or not even to your embedded system, also to any other firmware. For those things, you need to use open source tools. I mean, you can also do it with closed source, but it's really easy to do it, and it's available, and it's not like magic. First of all, you have to gather all those firmware samples that you want to research, that you want to do your work on, to do your emulation on. And this can be online via web pages, via FTP, via other possibilities, how the vendors provide their firmware, and also offline. For example, you can see here a picture of a TSOP flash chip, which is on an electronic device placed next to the main CPU. And with some electronic tools, you can extract the firmware and decompress it with software. So the next step is firmware extraction. You can use tools like binwalk, which automatically detect all those files and formats, and are also capable to decompress those files and formats. And the next step after that is determining the CPU architecture. So there are a lot of CPU architectures used out there in the embedded world, so Super H, ARM, MIPS, whatever. And the thing is, you need to cross-compile a right binary, a right firmware to run those binaries, which you gathered after the firmware extraction. And they are also sometimes depending on the library set, because for example, for ARM, you have also the hard float extension, and then you have hard float libraries and things like that. And you have to consider if you are compiling the kernel with the right flags and all those things, and with the right extensions and kernel modules. And yeah, that's sometimes a bit cumbersome, but it's possible. And if you do it on your own, first time, you will learn the most things. Next thing is compiling a firmware image for the target firmware. So I'm following the approach that I'm using change root, and I'm just compiling the right counterpart of the firmware, so the kernel and some tools, to place the sample that I want to emulate just in a change root inside the firmware. So like you can see here, I'm building the whole system, and after that I copy the whole content, the whole root file system of the firmware that I want to emulate into a change root jail. And from there, I just run it. And for those things, you can use QEMU and build root. So that's the perfect match if you want to emulate firmware. And it's not really complicated. It's complex, but yeah, if you want to tackle that on your own, you can just use the sample config files directly from build root, which are already configured to be used with QEMU. In the whole work, just Linux-based firmware images were covered, of course, because build root is just a build system for Linux-based firmwares. And I've discovered that the CPU architectures and instruction sets of those firmware images that I've collected from across 50 vendors were emulatable in 89%. So I've only had issues on 11% of those firmwares. And the reasons were different. So sometimes the instruction set was a bit different. For example, for a MIPS processor, there were some custom extensions, and it was not possible to run the firmwares, to run the binaries of the firmwares. And yeah, for that, I had just to skip the sample and go to the next. And same thing for unsupported CPU architectures, because sometimes you have CPU architectures like AVR, which are just partially or not really supported from QEMU or from build root. So sometimes it's just lack of support. And other issues are hardware interaction problems. So sometimes you have web servers which are a bit modified and access directly to a hardware endpoint in the proc file system. And yeah, for that it's also a bit problematic, but you have a solution for that. So that's a possible solution that I want to give at the end on this point, which is G-Ling. So it's a binary, advanced binary emulation framework, which you can use to emulate particular binaries and hook them. So that's really genius. And it's also possible to integrate it in emulated firmwares because it's you can run it via Python. The next thing is NVRAM, so the non-volatile RAM. Also sometimes a problem because NVRAM functionalities get accessed sometimes from the web server, from other programs which wants to load configuration strings, for example, or which want to store configuration strings. And you can circumvent that if you just preload a binary, a library, which contains all those functions. And with that, you can hook it, and yeah, then you can just spit back any string. Sometimes it works, sometimes it does not, but most of the time, the binaries for the web servers and the other programs on the firmware are okay with that. And one of the major things is an incomplete file system, because you can sometimes just download update packages from the vendor's website, which is a bit painful because you can download the whole system, excluding the web interface, and then you can start everything else, but web interface does not work, and yeah, your playground is much smaller then. And sometimes you have also distributed file systems, which is the case for some camera vendors from China. That's also manually solvable if you copy them together, but you have multiple partitions, and in one partition you have the pictures, in another partition you have the configuration files, and next partition you have some binaries, and you have to put all of that manually together, which is also a bit cumbersome, but yeah, okay, it's solvable at least. And the biggest challenge is if you have, for example, two interconnected operating systems, which is sometimes the case if you have LTE routers, because they have sometimes a real-time system for the LTE connection, which is connected to a Linux-based OS. And sometimes it's also Android, which is connected to a Linux-based OS. That's, yeah, not really cool and a bit hard to tackle, but yeah, one of the main challenges. So I want to start with my first example, which is from ProSoft Technology. That's a vendor for industrial Internet of Things devices and for automation devices. It's just an example that you can see how the emulation workflow works. And I had to do some tweaks. In that case, I just added one socket manually so that the web server was okay with that and that it was accessible afterwards. So let me switch to my console. That's now the QEMU string that I use to start the image. So that's basically the precompiled image where I've placed the whole content of the firmware that I want to emulate in a change route. And now it just starts up. It's getting the IP address 3.137. And yeah, I can interact now on a ARM processor, I think. Yeah, it's ARM 926. And if I want to change into my target firmware, my project is internally called Medusa, so that's the reason for the naming here. I just use this one, so that's now my new home, my change root directory where I can move around. And that's also at the same time the file system which is present on the target hardware. So if you would go now to the ProSoft Technology device, I don't know, ICX anything, and solder your serial port on it and access to the serial port and log into the device manually, then you would be able to see a thing like this, excluding, of course, my directories that I've put in here. And the first thing, what I will do is I will look for /etc. And you can see here, you have, for example, a profile script, which is very wise to be executed before you execute any binaries on the firmware, because sometimes you have whatever includes there that add something to the search path for binaries, and sometimes it's just setting a variable or whatever, and you would need it for executing the actual programs which are running on the firmware. And I have seen that that if I execute the content here in init.d, which is the first directory which content gets started, if the system starts up, then I will have reboot on one of the scripts. So I will just use this script started, which is obviously the HTTP. So you can see process started with executable stack. Does not really sound good, but okay. And now we can have a look on the process list, and we see that it is started and that it's using PHP 7. So the next thing is to look whether the IP address is configured right, is the case. And with netstat, you can, for example, look which ports are open. In this case, it's 8080. Just let us look whether it's reachable. And voila, it works. So I hope I have the right password at the hand. And yes, it works. In that case, I just had to add a socket here, which is the AT-CMD sock, because the web server looks for exactly this socket to communicate with other programs on the device to show their output on the web page itself. So all those things like link up, DDNS disabled, enabled, and whatever are things which are gathered from the system just by starting binaries. And yeah, for that, this socket is needed. Without, you cannot even do anything on the web server, because then it hangs all the time. And in the background, it pulls for exactly this socket. We can also have a look here with the utils. And for example, you can see it's process ID 255. Then you just would start strace with the process ID 255, and you are attached directly on the web server. And yeah, if I click on whatever configuration, you can see a lot of interaction. And in anywhere in this all of those strings, you will be able to see that it accesses to this socket, and that it pulls it, and that it needs some interaction with exactly /tmp/ and the name of the socket itself. Okay, so we have just started the binary and see that 2 ports are open. Let's see if we can open more ports. And for that, we go to configuration and advanced, I think, because there you can open more ports, or at least more services. In that case, it was enabled, but I just started the web server. So I have to disable and to re-enable it. And that's the thing with emulation, because you cannot always trust the web interface. But you can see Modbus is now open, and it would be possible to just interact with it to send messages via Modbus to the device. It's Modbus TCP. And the same thing is possible, for example, with Ethernet IP, which is also an industrial protocol, and enable it. And it works. So yeah, that's really nice, because in that case, you just can do testing on a fully emulated device. And for the if you have problems, if you have for example crashes of processes on the device, then it's always important to decide whether it's a problem from the emulation, which comes from the emulation, or which is really a problem of the program, because sometimes it's just crashing because it's trying to access I don't know any hardware which is not present on the emulation. Then it just crashes, and it tries to access to some file in the background which holds a configuration, for example, and It's also not present because it was an update file which you grabbed and which you tried to emulate. And of course, in that case, it's also not a security problem, but it's just a problem of the whole emulation. The next example, what I've brought to you in this talk now, is a real or a more industrial device. It's from Hirschmann, which was acquired by Belden, and it's for OT environments and for SCADA environments and for things like that. So that's in this case wireless access point. And you also had to do some tweaks. I also had to do some research on that. We had to collect all those init scripts which are placed in, you can see it here, which are placed in init tab. So just write the right command. And the init tab is also really important because all of the stuff which is marked here as sysinit gets executed if the system is booted. And you need to collect all of those lines. I just wrote a small script for that because it's really easy. So the syntax is really easy. And you just had to collect all of those lines and execute them one by one. And after that, in a lot of cases, it's possible to start up at least a few processes, sometimes all, but that's really rare. And in that case, I have done it. So I have collected all of the scripts in init. And this was placed in init. So all of those scripts are now here, and they get executed if you execute this one script. And it's running on this IP address, and it has those open ports. Now we have to look, and yeah, you can access to it if you know the right password, of course, which is set by default. And you can see there are problems. File system size, that's just anything, or available space, find K, or file and directory space used, can't K. So obviously you can see it's emulated. And sometimes there are a few problems if the system tries to access in the background to hardware, to some programs which may not work pretty well. And you can also see in the background, so that's the Hirschmann device, that you have a lot of output here. So it's everything which gets outputted from the system. And if you click around here, then you can observe that some commands will just pop up here. And that's really often the case also for other devices, for a lot of other devices. Also not OT and not SCADA devices, routers, access points, switches, managed switches, of course, and stuff like that, also webcams. And sometimes you can also observe that the programmer didn't do a really good job, because sometimes you can also spot debug messages here, which is also really nice to observe sometimes. Yeah, and those two devices were just emulated, and I have another two devices which also have vulnerabilities, which is also really nice. So just to say it in advance, those vulnerabilities were communicated to the vendors, and they were also disclosed. So you can find, for example, for Peppel and Fuchs, the link for the security advisory here. And yeah, in that case, it was the vendor Peppel and Fuchs, which which is creating devices for industrial IoT, OT, and much more. So a really broad field. And I combined 2 file systems in this particular case to get it work, because in that case I had one file system which was responsible to update the real system, so the real firmware, the BusyBox binary, and all the other stuff, all the other low-level stuff. And I had another file system which just contained the web server content and some applications and stuff like that. And the vulnerability, or I found other vulnerabilities too, but the vulnerability that I want to show you in this case was a command injection. And the vendor reaction was really correct. They fixed the vulnerabilities in time, and the advisory was disclosed afterwards. Okay, just switch to this one. So it's a rebranded device. That's the reason why the logo is different, but it's from Pepper & Fuchs. And you can see here that I've opened the MISC tab in the configuration tab. The device is running in the background here. And you can see all of the running processes. In this case, it's the HTTP server, this one. And it's also PHP, which is used by the whole system. And you can see here, you can create IO link. So it's a IO link master device. You can create IO link test events. And with those test events, we'll just open Burp in this case. I want to play around. And if you generate such an event, I've activated intercept, yes. Then you can see that it gets catched here by the interceptor. And if you just forward it, yeah, then nothing happens. And you can observe here that the response from the web server is, yeah, okay, PHP, and so on. But what if you just add a parameter like this and try to inject a command? In that case, the web server will just stay silent. And you can look in the background that there is a ping command which is running on the device. So that means you have found a command injection. And it's really easy to spot that on emulated devices, because obviously you have shell access. You can just observe if you were able to trigger the command. And in that case, the device had no shell access per default. So it wouldn't be even possible. I mean, it would be possible, but it would be really hard to find this vulnerability on a real device, because you would need to, as I said, soldier on the serial ports, access the console. Maybe you are able to access the system. Maybe it's deactivated, so that's also sometimes the case. And then you wouldn't be possible to find it. But in that case, it's really easy, because you can just spot the command which you have injected in Burp in this case. I mean, it's encoded in URL, but yeah, it's really easy. And you can immediately see that it is running also with the same rights in the same user context, of course, root in this case. And yeah, that's hard. The next example is Phoenix Contact. So I've done the same, basically. I've also done the same on a lot of other devices, but in that case, it was a bit harder to spot, because in that case, it was not PHP, it was a binary. So I I had to do a bit more research how to exploit it and see why it is exploitable. And for that, I've also used Ghidra. So I will just show you that you can really decompile, the whole binary, not really the whole binary, but at least 95% of the binary. So you can also see it's decompiled in pseudocode, and you can find all those functions. And yeah, it's possible to resolve the names and find all those strings which are embedded here, and so on and so forth. And if you look at the web interface, first of all, of course, back to the terminal. So it's running. It's running on port 443, and yeah, you can just see the processes here which are active, and you can just log into the device and see the web interface. And in that case, it's a really basic web interface where you can set IP addresses, where you can look up the IO status, which is not active on the emulated device, but okay. And you can also load configuration files. And I want to load such a configuration file, which I've stored during my preparation, and activate the interceptor. And then I click on apply, and you can see that the request is coming through. And in that case, you have to wait a little bit longer because yeah, the device is a bit slow in the background. And you see XML parsed, some strings are removed, whatever. Setup new config done. Please reboot next. And when I want to look up for vulnerabilities in the binary, in the CFG binary in that case, because you can see here that the endpoint is CFG, then you can just load it into a reverse engineering tool like Ghidra, and for example, look for dangerous functions. And there are a lot of functions which are used, but the first thing that I would look up is run shell, because yeah, that's sometimes vulnerable if it's used in a wrong way to command injection. And here you can just find references, and we're lucky. We're able to find some references on functions, and just bear in mind this string setup new config done, please reboot next. So yeah, does not look like that this string is here. Yeah, oh yeah, it is here. Please reboot next. And there you can see run shell, and yeah, %s, and it's directly concatenated to the run shell, so to the execute command actually. And yeah, that's a bad idea. And also the same thing applies to other locations where you can spot those run shell command. I mean, in this case, it was hard coded, but for the other locations, you can see that's again %u in that case, okay, but %s is also present here. And that means you can just append something to your file name. So that's the way how it would be possible. For example, typing in ls, and wait a bit because it's a bit slow. And in that case, you get out the whole content of the www/cgi bin/endpoint. So you can also see CFG, so the executable, the actual executable. And that way, it's also possible to execute commands here. And it would be also possible to pop up a reverse shell and all the stuff that you can imagine, because it runs as root and you have all the rights. So it was also possible to do firmware emulation on other devices. So you can see some sample pictures here, for example, Moxa, Red Lion, the Entron brand, or Advantech. It was possible for all of them to emulate the web interface and partially also the processes that are executed in the background, or which were opening ports like FTP, SFTP, SNMP, whatever. And sometimes, of course, it was also not possible just because the firmware was incomplete. So the main problems during creating a digital twin of the firmware is if you have incomplete file systems. So that's one of the main problems. Sometimes, so in 11%, if you can remember at the beginning of my talk, in 11%, you have unsupported CPU architectures, which may be sometimes the problem. With a lot of tweaking, you can add, of course, your own CPU architectures and maybe also a bit modified instruction set. Then you can increase the success rate. But all in all, I would say 10% are not really emulatable. And also the hardware interactions that you have. But as I said, you can use binary instrumentation tools like G-Link, which help you to emulate it anyway. And of course, vulnerabilities that were found during emulating all of the firmwares, yeah, you had all of them. So you had cross-site scripting, cross-site request forgery, sometimes even buffer overflows, command injection, and for all kinds of vendors. So sometimes, and that's really rare, you have vendors which have a real hardened firmware, real hardened system. So for those, it's not really possible to find any vulnerabilities because they have everything in place: cross-site scripting, protection, CSRF tokens that are changing on each request and stuff like that. And also things like binary mitigation measures, stack canaries, all the stuff. But very often it's not in place. And there are also binaries out there which are obfuscated. And yeah, I mean, it's sometimes security by obscurity because the researcher cannot dissect it and cannot say if it's secure or not. But yeah, that's also sometimes the way that the vendors want to go. So my personal next steps, and maybe also your personal next steps, because you just would need to bundle together QEMU and Buildroot, would be emulation of real-time systems, if it's possible. I have to do some research on it, but that would be really cool. Windows IoT, of course, that's a next thing which may be important in the future. More CPU architectures, so extending QEMU would be really nice, like Cavium Networks MIPS instruction set. So that's a thing which is partially supported, but which is not fully supported, and some extended hooks for NVRAM and other functions. Okay, if you have questions, I think we will have a 5-minute session now. My contact details are also printed here. Thank you.